last time we started talking about stereoisomers, right? So now, first off, what is an isomer?
Exact same
molecular formula, but different.
Right, same molecular formula, right? Now we had two different types of isomers that we've talked about at this point. So we talked about constitutional isomers. They had the same molecular formula, but they had different arrangement of atoms, right? And then we started talking last time about stereoisomers. So these are things with same molecular formula, right? Now we had the exact same arrangement of atoms, but how did stereoisomers differ from one another?
Like one's a wedge, one's a dash.
Right, so again, it's the same connectivity, but it's different arrangement in three-dimensional space. So the way that those atoms are connected to whatever they're connected to is different with respect to their arrangement in three-dimensional space, okay? So we talked about some basic types of stereoisomers. So we talked about our cyclic alkanes, right? Whether or not we had a methyl group that was pointing above the ring versus below, we called those cis-trans. We also talked about stereoisomers with respect to alkenes, right? Alkenes had carbon-carbon double bonds. And again, we were looking at the arrangement of the same group with respect to that double bond. If it was on the same side of the double bond, it was cis. If it was on opposite sides, it was trans, okay? All right, so then we moved into this idea, well, there's another class of stereoisomers, right? And this had to do with a concept called chirality. So if an object is chiral, if it's a chiral object, what does that mean?
That it has a mirror image of its own.
So everything has a mirror image, right? What is the big requirement to be chiral, though? So you do have a mirror image. Everything has a mirror image. But that mirror image, what does it have to be with respect to the original object? Non-superimposable, right? So to be chiral, you have to be, you have to be non-superimposable with respect to the mirror image, okay? Okay, so then we said, well, actually, molecules are going to be chiral sometimes, depending, okay? So we worked through this whole idea about what was going to make a molecule chiral, right? So we talked about carbon, right? Carbon specifically being SP3 hybridized, right? So carbon having 4 different bonds. What was going to make an SP3 hybridized carbon chiral? What was the big requirement?
4 different groups.
Right, so we had to have 4 unique groups that were attached to that carbon for our SP3 hybridized carbons to be chiral, okay? And so we went through and we identified chirality centers. That's what we call them when we actually have 4 unique groups. So these are chiral centers. Another word for this is stereocenters. And I use stereocenters a lot, so I apologize for that. But your book likes to focus on calling them chiral centers, okay? Okay, so now we'll start there. All right, so in this little molecule that I have here, we've got a carbon that's right in the middle, right? What is the hybridization state of this carbon? It's SP3 hybridized, right? So we've got our nice SP3 hybridized carbon. And then how many unique groups are attached to that carbon? We have 4 unique groups, right? So right here, we've got a chiral center. Right, so now we know that the mirror image of this guy is going to be non-superimposable on the original object. How would I go about drawing this mirror image? Let's say that my mirror is in front of my molecule here. So we have our mirror here, and I'm wanting to draw the mirror image of this molecule in that box. If we imagine that there is a mirror here, and this is going to be the mirror image, what part of this molecule are we going to see first in the mirror? What's going to come out at us first?
The one that's closest to the dash.
Right, so the one that's closest to the mirror is what we're going to see immediately over here. So if I start to draw this, I'm going to have a dash right here, all right? I'm going to have a wedge right here. The chlorine that's on the line is going to be going farthest away, and then the thing up top is going to be still up top, right? So this guy is the mirror image of our original object. And again, if we picked up our mirror image here and we tried to rotate it and superimpose it onto this guy, would we get the exact same thing? So we picked it up, we rotated it so that maybe the hydrogen would match up. If I did that, then what is going to be here if I'm trying to pick this guy up and place it on top? The eye, right? And so if we try to rotate this, we're never going to get the exact same thing. Okay, so again, this is our non-superimposable mirror image. Non-superimposable. Impose, I know, yeah. That's non-superimposed. I just say non-soup. That's it. That's what I should stick with, okay? Okay, so now, these guys, these non-superimposable mirror images, these are also stereoisomers. They have the exact same connectivity of atoms, they have the exact same molecular formula, but now their arrangement in three-dimensional space is distinctly different, okay? So because of this, these are two different molecules. So two different molecules. And most importantly, because they are non-superimposable mirror images, they have a distinct name to them, okay? So these are what we call, in organic chemistry, enantiomers, okay? So I'm gonna phonetically pronounce that, and I'm gonna write that on the board as well. So this guy, enantiomers, is spelled like enantiomers, enantiomers, okay? Okay, so again, non-superimposable mirror images of one another are enantiomers, right? So this guy, we'll call this molecule A, is the enantiomer of this guy. We'll call this molecule B, and vice versa. B is the enantiomer of A, etc. Okay? Okay, so one important thing to note about an enantiomer, for one molecule, there's only one distinct enantiomer for that. So there's only one mirror image of that molecule. So because of that, enantiomers have to come in these pairs, right? If you have a mirror image, that's your enantiomer if it's non-superimposable with respect to each other. Okay, so sp3 hybridized carbon, if we get a chirality center, that molecule with that chirality center is going to have one distinct enantiomer, one distinct non-superimposable mirror image, okay? Okay, so what's next? Now, we're going to have to learn how to draw the enantiomer of a molecule, okay? So let's say, for example, that I have this molecule here, and I want to draw the enantiomer of this molecule, okay? What is the enantiomer again?
The one character.
It is the non-superimposable what?
Image.
Child.
Sorry.
So non-superimposable mirror image of this molecule, okay? So if I want to draw the non-superimposable mirror image, what do I need to draw of this molecule? I need to draw its mirror image, okay? So there are a couple different ways that we can imagine a mirror so that we can draw the mirror image, right? So the first way that we are taught, at least the way I was taught when I was in college, was to imagine a mirror in front of the molecule, okay? So if I have a mirror in front of the molecule, and I'm wanting to redraw this molecule again, what am I going to see first in that mirror? Whatever is closest to the mirror on this side, right? So when I do that, we're going to see the NH2 first. It's going to go down and move away to the benzene ring, which is last. I'm really glad that he's doing that right now. It's a really good time. Now the question is, with respect to this methyl group that's on the wedge, how are we going to see that in our mirror? So if we have a mirror, it's right in front of this guy right here. And this side, we're coming out here. We're going to see the same thing coming out here, right? So our methyl will still be on the wedge in our mirror image that's in front. So we'll draw CH3. But now, when I pick this up and I rotate this molecule to try to put it back on top, what happens to that wedge? So again, if I try to pick this guy up,
It's not the same thing.
and I try to rotate it to put it back on top of this, so we're going to say rotate. So pick it up, I'm going to rotate it 180 degrees so that we'll get the benzene over here to NH3. Draw this guy. What was on the wedge now is what? Now it's on the dash, okay? So this becomes our CH3. Okay? Yes. Yes.
Wait, so which one would we have to write both?
No, you wouldn't have to write both, but both of these guys, this molecule and this molecule is the same.
Yeah.
All I've done is just rotated it with respect to one another. These guys, though, are the enantiomers of one another. So enantiomer.
So the one on the far right is not an
It is the answer. This is the far right is ideally the answer. If you had drawn this as well, it would have been an answer as well, because these two are the same exact thing.
So we can put either or on the exam, or you can ask for all.
You can put, so we're gonna go through this. There's another one. I'm gonna show you maybe a little bit easier to imagine the mirror, okay? And then long term, there's gonna be kind of an easy solution to this that hopefully will appear. Okay, so that's how I was taught, right? Is imagine the mirror in front, redraw the molecule, pick it up, rotate it. Is it superimposable? No, because for this guy, what was a wedge over here, and it's an enantiomer, is now a dash, right? So this is non-superimposable, mirror image, it's the enantiomer of the original object, okay? Now, another way that we can do this, and I'm gonna try my new little trick I learned. I'm gonna cut this right here, draw this back down here.
Well, that's cool.
Yeah, look at that, right? I just learned that this morning. Another way that we can imagine this is instead of imagining a mirror in front, we can imagine a mirror behind the molecule, right? So we imagine a mirror back here, and actually, I want to move this more. Move this, give me this, give me this. How did I make that move? Oh, there we go. Okay. Okay, so we're gonna imagine a mirror behind here, okay? So if I imagine a mirror behind, and I want to draw that mirror image of this guy behind the molecule, what can I do? I'm just gonna redraw the molecule, right? If we have this guy up front, I'm just gonna redraw the molecule behind. Oops. Benzene, up, NH2, right? So this is my mirror image of this, except now this guy was pointing out. What's gonna happen in the mirror image? It's gonna go back into the board. It's gonna become a dash. CH3, okay? So again, doesn't matter where you imagine the mirror when you're trying to draw the enantiomer. You can imagine it in front of it and draw the mirror image here, or you can imagine the mirror behind the molecule itself, redraw the molecule, except what happens? What was on the wedge now goes where? On the dash, right? And so regardless of the way we imagined our mirror, what was on the wedge, what happened to the enantiomer? Went to the dash, right? So long term, if we say draw the enantiomer of this molecule, you can just redraw the molecule. What was on the wedge is going to go into the dash, right? And vice versa. If we had something instead on the dash and the enantiomer, it's going to switch to the wedge. Okay? So if we have on our dash here, we're going to switch to the wedge. When we draw the enantiomer, if it was on the dash or the wedge, it's going to switch to the dash and the enantiomer.
And that's only on this mirror, right? Behind.
It's on all of them.
Okay.
If I tell you to draw the enantiomer, just switch to wedge and dash.
Okay.
Long term. So this ideally is like the perfect scenario when they give you these wedges and dashes and it's kind of easy to see. Sometimes it's not, but for the most part, this is kind of like a tried and true method. If I give you a molecule and I say draw the enantiomer of this molecule, just switch the wedge and the dash. Okay, so I've given you guys a couple problems here where I want you to draw the enantiomer of a molecule, right? And hopefully, I made it clear kind of in the previous examples that you don't necessarily have to always go about, imagining a mirror in front or imagining a mirror below, etc. You can kind of just, cheat and switch your wedge and dashes, really, right? Now, that doesn't always work, and I do want to specify that. If you do have a chiral center and you do have a wedge and a dash, you can just switch the wedge and the dashes if you want to draw the enantiomer, but sometimes that's not always going to be the case. So just note that, it's maybe safe to go back once you've drawn your enantiomer and imagine it actually being the mirror image in some form, okay? Okay, so I'm going to go ahead and I'm going to start with this molecule, right? Right now, it's important to denote the chirality centers, right? So we're looking for sp3 hybridized carbon with 4 unique groups around it. For this molecule, there's only one. It's right here. And again, usually, if it is a good question, and it is a chirality center, there will be a wedge and a dash, right? So if there's something that has a wedge, something that has a dash, that could be a big helpful hint that that's the chirality center that you're actually dealing with, okay? All right, so I'm going to take this guy, and I'm going to go ahead and redraw kind of like the skeletal structure of it, ignoring the whole wedge dash thing. So we've got our, this is ugly. We've got our aromatic group. We've got oxygen, an alcohol, and alcohol. We've got our alternating double and single bonds. We've got a mountain to a bunch of methyl groups, and then this guy has a hydrogen attached. Okay, so that's kind of like the basic structure. That stuff's really not going to change if we try to draw the mirror image. If we drew the mirror image and we imagine the mirror here, then yes, this would like rotate differently. But if we were imagining the mirror image as being somewhere in front, then it would be the exact same thing, okay? All right, so now all we have to do is focus on this guy. If this was on the wedge and we wanted the enantiomer, then whatever is on the wedge, we're going to move to the dash, right? So we do have an implied hydrogen here. That's what's on the dash. But again, we don't have to draw that hydrogen. It's there. We know it's there. It's the fourth unique group. All I really have to focus on is what they give me, which is this methyl group, right? So if this was on the wedge in the original molecule, I want to draw the enantiomer. I just need to move that methyl group to the dash. And that's it. So same thing for this guy. I'm going to just redraw my original structure, or the backbone. Again, we're looking for our chiral center here. They do give us a dash here, so that tells you, if you look around this guy, this carbon is attached to a nitrogen. It's attached to a carbon that has an alternate path. It's attached to a carbon. These guys are different, right? And then there is a hydrogen that is implied, that's coming out. So I'm going to go ahead and just redraw the kind of skeletal structure. This is going to go there. I'm going to draw this solid because it helped me draw the 5-membered rings. I'm not the best at them, and then I'll come back and erase that. Okay, so I'll go ahead and fill in everything else. Again, this is our chiral center. In our original molecule, it had that ring going into the board. So in the enantiomer, that ring is going to come out, right? And we're going to draw that via a solid line here. This also has a methyl group. And so maybe you can make that prettier than I can. And maybe make this nice and thick to really denote. That's really ugly. So I'm gonna erase this because this now it's irritating me. But again, trying to denote that spatial arrangement. This guy is our wedge. It's coming out. It was going in. On the original molecule, the enantiomer of that is going to have that ring coming out. Okay, so go ahead. Hopefully you guys got practice doing that. And I think there's probably more in the homework. I have to check that to remember. But if we want the enantiomer, you can imagine a mirror. You can imagine it in front. You can imagine it below. You can imagine it behind. Regardless of what you do, though, usually what you're going to see in drawing the enantiomer is just switching wedges and dashes. We also, when we talk about them and name them, we have to be able to distinguish the actual three-dimensional arrangement in the name, okay? So, for example, if I wanted to name this molecule, how would I start?
The parent.
The parent chain, and so this chlorine as a substituent is named chloro. So just note that it's going to be the same thing as a methyl and ethyl or anything like that. Our parent here is what? We have 1, 2, 3, 4.
Butane.
So this is butane, right? If chloro is a substituent, what position is it at? 2. So we would name this 2-chlorobutane. What would we name this molecule? 2-chlorobutane as well. So this would also be 2-chlorobutane. And so this is like my argument for why denoting the configuration of this is important. These are two distinct molecules. They are not the same molecule. We have to be able to denote that when we actually name them, right? At the point that we're at right now, they have the same name. So we have to be able to say, well, actually, in this molecule, we've got our chlorine coming out of the board. In this molecule, our chlorine is going to be going into the board. Okay, so how are we going to do that? That's what we're going to talk about next. Okay, so what we're going to do is we're going to designate what is called the absolute configuration about our chirality centers. Okay. Okay, so to do that, we are going to use a system of rules that is called the Kohn-Ingold-Prelog system to denote configuration. It is named after Kohn, Ingold, and Prelog, who were the ones to devise this system. Okay, so just note that this is our IUPAC system. This is how we're going to denote configuration about a stereocenter. Okay, so again, with respect to organic chemistry, we love to have these nice little system of rules that we're going to put in place so that we can make sure that all of our configurations are denoted the same. So our system of rules under the Kohn-Ingold-Prelog are as follows. Okay? So first off, the first thing we're going to denote is the fact that we have a chirality center and where it's at. The second thing we're going to do is we're going to look at the atoms that are directly attached to the chirality center, and we're going to organize or prioritize them with respect to decreasing atomic mass. And I'm going to go through this, and we're going to go through a lot of different problems to do this. Once we have prioritized the atoms that are attached, we are then going to manipulate the molecule so that the fourth priority goes on the dash. And then we're going to see, in going from 1 to 2 to 3, are we going clockwise or are we going counterclockwise? And that's going to depend on how we actually denote the configuration. We're going to go through a lot of examples to do this, okay? So I just show you these to say this is what we're going to be doing. These are the 4 rules or the 4 steps involved. Okay, so let's try one to actually see how we're going to do this, okay? So I have a molecule here, and my first step in denoting the absolute configuration is first off identifying the chirality center that we're actually trying to denote configuration for, okay? So I'm looking at this guy. Where is my chirality center? Where is my carbon, sp3 hybridized, that has 4 distinct groups on it? Right, so if we have, look at this guy, right? We have a chlorine attached to that sp3 hybridized carbon. We've got an ethyl group, right? We've got an ether group, which is different, right? So that's 3 distinct groups. Where is the 4 distinct unique group? Right, so we have a hydrogen that is coming out of the board on the wedge, okay? So these are our 4 distinct unique groups. This is our chiral center. Okay, so now what we're going to do is we're going to look at the atoms that are directly attached to this carbon, right? So up top, we have a chlorine that's directly attached to the carbon, right? So we can go ahead and write chlorine out here. We've got a hydrogen that's directly attached to the carbon, so we can write hydrogen out here. What is this guy? What is directly attached to that chiral center? What is this atom? A carbon, right? So this is a carbon. So we can write a carbon out here. And then over to the right, we've got what? That's directly attached. Oxygen, right? And so we can go ahead and write oxygen out here, okay? So now we're going to prioritize these guys with respect to decreasing atomic mass. So number 1 is going to be the heaviest element up there. Who is the heaviest element in order of atomic mass? Chlorine. So chlorine, we'll note, is 35, has an atomic mass of 35. So because of that, it is heavier than everyone else. We're going to give this priority number 1. It's going to be number 1. Who comes next?
Oxygen.
So next is oxygen. If we look at the atomic mass of oxygen, it's 16. So we're going to give this number 2. Who's number 3?
Carbon.
Carbon is 12 AMUs, so this is number 3. And then who is number 4, final? Hydrogen. Okay?
Hydrogen's always going to be number
Yeah, hydrogen's always going to be number 4. Well, not always, no.
4. Wait, what else?
There could be carbons that don't have a hydrogen attached to it and still be a chiral center. There's an example of it later on. But if there is a hydrogen, it will always be number 4. Okay, So same exact thing down here, let's say. So where is my chiral center on this molecule?
Right there.
Right there, right? So again, we've got a carbon that has 4 unique groups. We've got a hydrogen that's on the dash. Who would be given number 1 here?
Sulfur?
So sulfur, if we look down on the periodic table, sulfur's at 32. So it would be number 1. Who would be number 2? So we look at fluorine. Fluorine's at 19. It would be number 2. Who's number 3? Who's over? We have hydrogen versus carbon, right? So carbon would be number 3. And then who would be number 4? Hydrogen. Okay. Okay. So always looking at the atom that is directly attached to the chiral center, not the entire thing that's attached, just specifically the atom that is attached, okay? All right, so that's number 1, prioritizing, right? Now, once we have our priorities, what are we going to do with them? So what we're going to do, now that we have prioritized these guys, is we're going to take this molecule and we're going to do whatever we need to do to it to get number 4 on the dash. Okay, so what I mean by that, I'm going to go ahead and take just this bit of the molecule because that's all I really care about here. And I'm going to redraw that. So we have 4 up here, we have 1 right here, we have 3 here, and we have 2 here, okay? I want 4 to be on the dash. I need it to go into the board. So what do I need to do to this molecule to get 4 on the dash?
Mirror image.
Can you switch 1 and 4?
You can, but let's just focus on, we can rotate it, right? Right, if we pick up this molecule and we rotate it 180 degrees, 4 will be on the dash, right? So if we just pick this up and rotate, we'll be given the exact same structure, except now 4 will be on the dash. What will be on the wedge if we pick it up and rotate it? 1 will be on the wedge. Now, what will be on the left-hand side? If we pick this up and rotated it, on the left-hand side will be 2. And then on the right-hand side will be 3. Okay? Okay, so we prioritize, and then we rotate or manipulate the molecule so that 4 is on the dash. Now, we're going to ignore 4 entirely. So 4 goes away, just ignore it. And we're going to say, okay, in going from 1 to 2 to 3, are we moving in a clockwise direction or a counterclockwise direction? So here we go from 1 to 2 to 3. Is this clockwise or counterclockwise? Right. So going for this molecule in 1 to 2 to 3, we have to move in a counterclockwise direction. So counter. If we have to move in a counterclockwise direction and going from 1 to 2 to 3, then we denote that with the configuration of S.
By the numbers is what?
You're looking at 1 and going from 1 to 2 to 3, ignoring 4 entirely. How do we get from 1 to 2 to 3? Do we have to go in the clockwise direction, or do we have to go in the counterclockwise direction? Okay, if it's counter, then we denote that with the configuration of capital S. So capital S stands for sinister. So sinister in Latin means left-handed. That's no joke. Sinister means left-handed in Latin.
That's right.
Okay, so if we utilize the other molecule that we had on the screen on the previous one, which had the fluorine, the sulfur, this was a 1 to 2 to 3 to 4 here. So 4 for this guy was already on the dash, right? So we don't have to manipulate it at all. And going from 1 to 2 to 3 for this one, how do we get there? Is it clockwise or is it counterclockwise?
Clockwise.
This one is clockwise. So because this is clockwise, we call this R. And R stands for rectus. So rectus, which again is Latin. And I do have a little point with this. So rectus means right in Latin, but right-handed in Latin is dexter. So, you know, sinister is left-handed. You would think, oh, D for dexter, but it's no big deal. Okay, yeah.
So in order to rotate it, you want the biggest molecular to be number 1 or to be closer?
No, so you want the less one, number 4, whatever the 4 is, it has to be on the dash.
Okay.
4 has to be on the dash. You're going to do whatever you have to do to get 4 on the dash. It has to be going into the board.
And that's why you rotate.
That's why I rotated it on the original one. And we'll talk about, there's some tricks that you can do where you don't have to rotate things if you don't like to do that. Okay. Okay, so that's it, right? We identify our chiral center. We prioritize the groups according to decreasing atomic mass. We manipulate the molecules so that 4 goes into the board, and then we see, in going from 1 to 2 to 3, are we going in a clockwise direction or in a counterclockwise direction, okay? So it seems fairly simple, right? Not too hard. Now, the question comes, what if in that atom that is directly attached to our chiral center, what if we have the same exact atom? Right, so for example, right here, we've got our chiral center right here, right? We've got an oxygen attached to it, we've got a hydrogen attached to it, but then going in left to right, what is the immediate atom that's attached to our chiral center here? It's a carbon on this side. What is it on the other side? Same thing, right? So now the question is, okay, well, I know who number 1 is. Number 1 is the oxygen, because it's going to beat carbon, carbon, and hydrogen. So we can already do this one. I can also say who number 4 is, because hydrogen is going to be less than all of these. But now the question is, who is 2 and who is 3? And how am I going to denote? Or how am I going to figure that out, okay? So now what we're going to do, if we have a tie with the atom that's directly attached to the chiral center, we're going to see who that atom is attached to, okay? So if I look at this atom, right, who is this forming bonds with? We have a bond to a carbon up here, right? Who else is it forming bonds to?
A hydrogen.
2 hydrogens, right? So we have a bond to a hydrogen and another bond to a hydrogen, okay? So that's what this next guy is bound to. What about this guy, right? This guy is bound to a, who is this bound to?
Another carbon.
A carbon, right? And then also, who else? A hydrogen and a hydrogen, okay? So what we're looking at is our first point of difference. Between these 2 atoms and who they're bound to, do we have a difference between them at all? No, right? So what do you think is going to have to happen next?
Go to the next one.
We're going to go out to the next one, okay? So the next one for this guy is this guy. Who is this one bound to?
Another carbon.
We have a carbon here, right? So we have a carbon, and then we have how many hydrogens? A hydrogen, okay? So that's that guy. What about over here at this guy? So this is my next one out on my left side. Who is this attached to? We have a bond to a carbon. We have a bond to a carbon, and then a hydrogen. So this guy is carbon, carbon, hydrogen. Do we have a point of difference now?
Yes.
Yes. So carbon versus carbon here is the same, but now carbon versus hydrogen, who has the highest atomic mass? The carbon. So because of that, that first point of difference, this side is going to get 2. Let me make that more distinct. This is 2, and then this guy will get the 3. So overall, we'll be left with 2, 3, and then 4 and 1. Okay, so same thing, and I just want to make one more note with respect to this. It is the first point of difference and not the overall atomic mass of the group that's attached, okay? So in a similar situation down here, we again have an oxygen-hydrogen, which will be our 1 and our 4. Going out, we've got a carbon and a carbon. Again, that's not going to give us anything, but moving out from them, seeing who they're attached to is going to define who the next priority is, right? So if I start on my right side, who is this guy attached to? A carbon, and a carbon. So carbon, carbon, carbon. Who is this guy attached to? We're attached to an oxygen, and then a hydrogen and a hydrogen. There is tendency to say, oh, well, carbon, 3 carbons is like 36, and then an oxygen and 2 hydrogens, that's like 18. So the 3 carbons have to get the priority. It's not. It is the first point of difference. Our first point of difference came between oxygen versus carbon. Who has a higher atomic mass? Oxygen. Okay, so because of that, this will get number 2, this will get number 3. It's not the entire group that's attached, it's literally the first point of difference. Okay, yes?
I just want to make sure you lost me a lot in that first top one up there, because
Yeah.
you saw a lot. But is it because Is that one too because it splits into a CH3 faster than the other side? Like you said, it's like immediate difference, or?
No, so yes, kind of. It's more of when we started here at these carbons, we looked at, okay, who are these two carbons, which are the two competing with one another, who are they attached to, right? When we looked out, we said this guy's attached to this carbon, and it's attached to two hydrogens. So we had a carbon, a hydrogen, a hydrogen.
Yeah.
We looked at this guy, it was the same thing, right? It was attached to a carbon and then two hydrogens. So at that point in time, we can't decide. So then we move out again. Moving out again, we're going to compare this carbon to this carbon, right? And so for this carbon, who is it attached to? A carbon, a hydrogen, a hydrogen. Who is this carbon attached to? A carbon up, a carbon down, and a hydrogen. So here we have a competition between carbon, carbon, hydrogen versus carbon, hydrogen, hydrogen.
Okay.
That first point of difference is the carbon, and the carbon will win.
All right, now I see it. I didn't note that, I forgot about that top carbon there.
Yeah.
And so I was like, why there? But now I see it. Okay.
Okay, so then one more little thing to note. Again, we're looking for first point of difference. The only other thing I haven't mentioned is what happens if we have a double bond. Okay, so example, let's say that we have a chiral center here, right? So if we look at this molecule, this is our chiral center. If we go out trying to prioritize, if we go this way, who is this guy attached to?
Okay.
A carbon, right? If we go this way on the wedge, who is the chiral center attached to directly? A carbon. This way, a carbon. This way, a carbon. So that first atom out, we can't tell anything, okay? Now, the question is, who are these individual carbons attached to? So for the one that's on the, let's say this guy, the one that's on the wedge, who is this carbon distinctly attached to? It's attached to 3 hydrogen, right? So this guy would be a hydrogen, hydrogen, hydrogen. What about this guy? This guy's attached to a carbon and then 2 hydrogens, right? So carbon, hydrogen, hydrogen. What about this guy? Again, a carbon, hydrogen, hydrogen. Now the question is this guy, right? This guy has a double bond to an oxygen. How are we going to treat that? We're going to treat it as 2 single bonds to oxygen. So we would say that this carbon is attached to an oxygen, and then who is this last guy? A hydrogen, okay? And so now the question is, first point of difference, can we tell for any of these? So we've got an oxygen versus a hydrogen versus a carbon versus a carbon. Do these differ in atomic mass?
Yeah.
Yes. Who is the heaviest?
Oxygen.
Oxygen. So oxygen would get 1. Between carbon and hydrogen, who's heavier?
Carbon.
Carbon. So these guys out here are going to compete between 2 and 3. This guy will be 4. Okay? Now for these two, how would I figure that out?
Go to the next one.
I'd have to go out to the next one, right? Next one would be hydrogen, 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 carbon, hydrogen, hydrogen. This guy would get a 2. This guy would get a 3. Okay? Okay, so now really quickly, I want to note one more thing. If I take this guy and I go ahead and just draw the chiral center the way it's been drawn on the board, and I go ahead and write my priorities in. So for this guy, we had a 1 out to the right. We had a 3 up at the top. We had a 2 on the dash. And we had a 4 on the wedge. After prioritizing, I need to manipulate this so that 4 is on the dash, right? But that would be that's a little bit difficult with this one, right? Because, well, it's not super difficult, but what would I have to do to this guy if I want to make 4 on the dash?
Rotate it first.
I have to rotate, but I need to rotate only in a specific way. So let's say we do that. We have dash here. We've got a wedge. So 4 will be here. Now who will be out to this position on the right?
1. Oh.
So we're only like rotating maybe like 120 degrees here. So then if 4 is on the dash, then 2 is going to be out here. So 4, 2, and then 1 will be here, and then 3 will be here. Okay? Now, for me, that's very difficult to do, and I don't like to do that. I don't like to manipulate things in space. So there is another trick that we can use that will ensure that you get the correct configuration, and it ensures that 4 goes onto the dash, okay? So what we're going to do is we're going to take this original molecule, I'm going to redraw it. And what we're going to do is we're going to trade whoever is on the dash with number 4. Okay? So for this guy, 2 is on the dash. We're going to put 2 wherever 4 was, and we're going to put 4 on the dash. Okay? Now, when we do that, we actually invert the configuration. So for whatever it was, we've turned it into the other thing. Okay? If we want to get back the original configuration, that's fine. All we have to do is switch the other 2. Okay? So in doing that, we would have, to get back to the original configuration, 4 would be here, 2 would be here, but then we would also have to switch these guys. So this will be now 1, this will be 3. Okay, so if we have this and we're like, I don't want to rotate this, I don't want to do this, all you have to do is first switch whatever 4 is with the dash position, okay? That inverts the configuration. To get it back to the original one, you then have to switch the other 2. Okay, and now this will be the exact same thing as if you rotated it, you would get the exact same configuration, okay? So if we go from 1 to 2 to 3 for this guy, which direction are we moving in? 1 to 2 to 3 is going counter, so this would be what? S, right? If we look at this guy too, and going from 1 to 2 to 3, what are we doing?
Same thing.
Same thing, it's S, regardless. You can rotate it, you can manipulate it, or you can switch and then switch. You'll get the exact same configuration regardless. Yes?
Now, how do I know if it's going clockwise or counterclockwise? Because the wedge is pointing, like, so.
You're literally looking, you're ignoring 4 entirely, and you're saying, in getting from 1 to 2 to 3, do I have to go clockwise or do I have to go counterclockwise?
Okay.
Ignoring the dash. I keep saying wedge, I think. Maybe I don't. I don't know. And then I've left behind some junk from before. Okay, so again, that trick is switch 4 with whatever is on the dash, right? That inverts the configuration. If we want to get back to the original configuration, you have to switch the other 2 groups as well.
But if we don't want to get back to the original configuration, just leave it alone, like just switch the 3 and the 4, or the wedge and the dash.
So the idea behind this is we're doing this to figure out what that original configuration was. So this trick is to say, hey, if I switch these, because sometimes that's easier, I've inverted it. If I want to see what the original one was again, I have to switch the other 2 to get back. Because again, we're trying to assign configuration to this guy, so we need to be back in the original configuration to do that. So switch, but then switch.
It took me a second to understand what was going on here. Like, oh, okay, I see.
The whole idea behind this with the S and the R, right, is that by giving you, this is the S enantiomer, you can know who is attached to who and what arrangement they actually have in 3-dimensional space. And that's the purpose of this system, is saying there's 2 distinct ones. One's R and one's S. Their enantiomers are one another. R is configured like this, whereas S is configured like this. Okay, so we have a little bit of time left. I'm going to do an example, and then we'll do a few to get some experience with this.
Are we taking the quiz home?
We have still lots of time.
Oh, okay.
Yeah.
Sorry.
Lots of time, Dean. Okay. Okay, so I have a molecule here, okay, and I have one chiral center in this molecule, and I want to know, is this chiral center R or is this chiral center S? Okay, so we're going to utilize the rules that we have just learned to denote that. All right. Yes.
You said you have one chiral center? I
Yes.
see 2.
Why? Where's the other one?
Where the O is?
Which one?
Under the O. So I have an octuple. Oh, never mind. I saw that.
Okay, chiral center, only one, right? Again, it has to be SP3 hybridized, and it has to have 4 unique groups attached to it, okay? So this is our chiral center. We've got, again, a hydrogen out here, so that's helpful just to note when we're prioritizing. Now that I've found my chiral center, I'm going to go through and I'm going to prioritize based on atomic mass, okay? So as a helpful little hint, I don't like redrawing molecules, and you don't have to do that for determining configuration. All I'm going to do is take this part and redraw it out here so that I can keep track of everything much, much easier, okay? Okay, so when we're looking at the atom that is directly attached to the chiral center, we're comparing a nitrogen to a hydrogen to a carbon to a carbon. Who has the highest atomic mass?
That carbon is attached to
Nitrogen.
O, so that's gotta be 3.
So who has the highest atomic mass? Highest atomic mass is nitrogen, right? Nitrogen's right above carbon on the periodic table, right to the right of it. So this guy's going to get a 1, right? That's number 1. Who's going to get 4? H, right? For this guy, there's an H involved, so that will always be 4 if there's an H involved, okay? So we can go ahead and say, all right, I got 1 here, and I've got 4 here, okay? All right, now we're comparing this carbon to this carbon. They are the same thing, right? So we can't tell the difference between those two. Now we have to go out to the things that they're attached to. If we start on the right with this guy, who is this attached to?
The other carbon.
It's attached to a carbon over here, and then it's attached to 2 hydrogens, right? So we say carbon, hydrogen, hydrogen. If we go over here, who is this carbon attached to? We've got a double bond to an oxygen, so that's going to count as 2 O's. So O, O, and then this one is another O. Just the atom, not who the other thing is attached to. All right, do we have a point of difference?
Yes.
We have, first thing we come to is oxygen versus carbon. Who is heavier, or who has a higher atomic mass, oxygen or carbon? Oxygen. Right, so because of this guy versus this guy, this side is going to get the 2, and this side is going to get the 3. Okay, so we can go ahead and say 2 and 3. So now we have prioritized. What's next? Manipulate, right? So what do we need specifically to happen before we can assign configuration?
4 needs to be
4 needs to be swapped, right? 4 needs to go on the dash. So again, there's 2 ways to go about this. If I want to just rotate this molecule to get 4 on the dash, what do I need to do? I just need to pick it up and rotate it 180 degrees. When I do that, we'll have 1 here. We'll have 4 here. What will happen to these other 2, the 2 and the 3, though? They'll switch, right? So this will be a 3, this will be a 2. Again, though, we don't have to do that mentally, right? All I have to do is switch 1 and 4. So if I switch these guys, so switch so that I have 1 here, I have 4 here, that inverts my configuration. How do I get back to the original configuration? I have to switch these guys, right? So 3 and 2. Same thing regardless. For me, this is easier because I have trouble with spatial arrangement. It's hard for me to imagine picking things up and putting them down. So I know that if I switch these 2, that's fine, but to get back to the original, I also have to switch the top 2. And I get the same thing regardless. Okay, so now once we put 4 on the dash, what do we care about now?
If it's S or R.
Right, and so how am I going to determine that?
1, 2, and 3.
I'm going to look at how I get from 1 to 2 to 3. Right, so when I go to 1 to 2 to 3, how do I get there? Do I move in a clockwise direction or a counterclockwise direction? This is counter. And so if it's counter, then what is this configuration? S.
Or sinister.
Sinister, left-handed. I know, it's so sad.
I know.
That's why it's fun to take Latin. You learn all of these little dexter, because like dexterity is a good thing, right? Oh, they're so dexterous. Or, yeah. That's it. That's how you assign configuration, or absolute configuration, to a chiral center. Okay? Oh, look, we have 17 minutes left.
We don't have
Ask
enough
questions.
time.
Ask questions.
Yeah,
I think we should practice this.
Oh, yeah, we should probably. Oops. Okay, so here's some practice problems I'm going to have you guys do. I would spend some time with these. There's a lot of them, right? So in each molecule, number 1, the first thing you guys have to do is identify the chiral center, and then I want you to assign it either the absolute configuration of R or S, okay? So I'm going to go ahead, I'm going to start on the first one. If you want to give that a try, I would pause the video, and then we'll move on to the others. So if again, go ahead and give some of these a try, pause the video, and then come back for the answer. Okay, so in number 1, again, the first step in assigning absolute configuration is determining what centers are actually chiral centers, right? And so as a reminder, for a center to be chiral, it needs to be SP3 hybridized, and it needs to have 4 unique groups attached to it, right? So if I'm looking at this first molecule right here, I'll note that I've got a couple of SP3 hybridized carbons in here, right? I've got 1, I've got 2, I've got 3, 4, 5. These guys are both SP2 hybridized carbons, so I'm going to ignore them. But note, a lot of these guys don't qualify for that 4 unique group, right? For example, these methyl groups just have hydrogens attached, right? Those are not unique, those are the same. Same thing for this guy. It's got a hydrogen, but then it has 2 methyl groups. These things are not unique, so essentially it doesn't have that 4 unique group. All right, so then last, we come to this center right here. We have a carbon that's attached to a chlorine that's coming out at us on the wedge. That means that, again, since carbon has to have 4 bonds, there is an implied hydrogen, and that implied hydrogen has to be on the dash. It's going in. So that's 1. We have 1, 2, and then this is a carbon, this is a carbon, but these guys are not the same thing, right? This and this are different, and so because of that, these are the 4 unique groups, right? Because those 2 substituents or things that are coming off that carbon are different, okay? Okay, so that this is our chiral center that we need to assign configuration for, okay? So now what I tend to do is I tend to kind of leave the molecule behind, and I only take that little portion of the chiral center that I'm actually trying to determine configuration for, all right? So all I'm going to do is essentially redraw this, and I'm going to draw it in terms of actually assigning priorities, okay? So if I am assigning priorities here, we're going to number these guys. Again, the thing that gets the highest priority, or the highest number, or number 1, I guess is not the highest number, is the thing that has the highest molecular mass, or the highest atomic mass, right? So if we're comparing these guys, we've got chlorine versus hydrogen versus a carbon versus a carbon, right? So chlorine's like 35 AMUs. It's going to get number 1. It has the highest atomic mass. There's carbon and carbon, so they're tied right now. We'll come back to them, but they're both going to be heavier, I guess, than hydrogen, right? So hydrogen is going to be assigned our last priority. It's going to get number 4. Okay, so then we're going to come back to these guys, right? We had a carbon and a carbon, right? Now, because there's a tie there, we have to move out to who these carbons are attached to, and again, we're looking for our first point of difference, right? So, for example, this carbon right here is attached to another carbon, it's attached to a carbon, and it's attached to this implied hydrogen that is also there, all right? So this guy is attached to a carbon-carbon hydrogen, whereas over here, for this guy, right, we have a bond to a carbon, and then we have a double bond to a carbon. And anytime we have a double bond to something, we're going to treat that as 2 single bonds, right? So this guy is attached to a carbon, and then a carbon, and then a carbon. We're looking for first point of difference. So the first point of difference comes here, right? Carbon has a higher atomic mass than hydrogen. Since that's going to be the first point where we differ between these 2 sides, this guy's going to get the highest priority because of that, right? So this one, we're debating right now who is 2 and who is 3. This side is going to be 2. This side is going to be 3. Because, again, that first point of difference, we had a carbon versus a hydrogen. Because carbon has a higher atomic mass, this guy wins. Okay, so once we've assigned priority, we need to either rotate the molecule or manipulate the molecule so that 4 is on the dash going into the board. We don't have to do anything for this guy because 4 is already on the dash. So now we're just looking at how do we get from 1 to 2 to 3. We're just going to ignore 4. To go from 1 to 2 to 3, we have to move in a clockwise direction. And clockwise is R. So the absolute configuration here for this center is R. Okay, so same thing over here. Again, we're looking for a chiral center. We need 4 unique groups. This guy is going to be our chiral center. We have a carbon that's attached to a methyl group. It's attached to an ethyl group. It's attached to a chlorine. And then again, on that dash going into the board, there's a hydrogen. Okay, so same thing. I always like to redraw because that's just what I do. This is a very similar problem to what we just saw. I don't want to do that. So chlorine, between chlorine versus hydrogen versus carbon, chlorine is going to have the highest atomic mass. It's going to get top priority. Again, hydrogen, carbon, hydrogen's always going to get 4 for the most part. And so then the question is, okay, we have 2 carbons. There's a tie there. Who's going to win that, or who's going to beat the other to get 2 versus 3? Because these guys are tied, we have to move out to who they're attached to. So this carbon is attached to another carbon, all right? So we have a carbon, but then it's also attached to 2 hydrogens. Whereas this guy is only attached to those 3 hydrogens, right? So this guy's got bonds to hydrogen, hydrogen, hydrogen. Again, for first point of difference here, we immediately hit a carbon versus a hydrogen. Because carbon has a higher atomic mass, this guy gets the highest priority. So this is going to be 2, and this will be 3. Again, 4 is already on the dash, so we don't have to worry about that. We're just questioning how do we get from 1 to 2 to 3. Again, this guy is clockwise. So this is also an R. So those two are very similar with respect to one another. Okay, moving over to this third molecule. Again, we're looking for our chiral center. We're looking for 4 unique groups around sp3 hybridized carbon. When we look for that, we're going to find that here. For this one, we have an amine group, right? This NH2, this amine group on the dash. Again, carbon has to have 4 bonds. So on the wedge, there is an implied hydrogen. We can go ahead and draw that. And then, again, I'm going to go ahead and just redraw the molecule. Hold on. And I'm going to assign priorities to everything. Okay, so for this guy, we have carbon. This is our chiral center. It is attached to an oxygen. It's attached to a carbon. It's attached to a nitrogen. It's attached to a hydrogen. All right, so this is nice and easy because we can just assign it immediately. We don't have to go through any type of tiebreaker process. Oxygen has an atomic mass of 16, so it's going to get number 1. Nitrogen has an atomic mass of 14. It's going to get number 2. Carbon has an atomic mass of 12. It's going to get number 3. And then hydrogen is 1. It's going to get number 4. Okay? Okay, so now this is the first time where we don't have 4 or the least priority group on the dash. So we're going to have to do something to get it there. And so there are 2 things that you can do, right? First off, you can just rotate the molecule, right? So if you're good at imagining things in 3-dimensional space, if we took this molecule and we rotated it 180 degrees this way, right? So like flip it essentially. Then what we'll be left with, we get 4 on the dash, right? 2 would come out on the wedge. And then because we flipped it, 3 and 1 would have switched places. So that's one way that you can do this. The other way, which is what I actually prefer, because I don't do well with imagining things 3-dimensionally, is you're going to switch places with 4 and whoever is on the dash, right? So right now what's going to happen is I'm going to say, okay, here's 4. It's on the wedge. I'm going to switch its place with the number that's on its dash, right? So that happens to be 2 in this situation. So when we do that, we can go ahead and switch these guys. So we're going to switch these. Oops. So now 4 is going to be on the dash. We're moving 2 to the wedge. By doing that, what happens is we actually invert the configuration. So whatever it was before, whatever we're trying to solve for, by doing just switching one of the 2 of those places, we change it to the other configuration. So now to get it back to what it originally was, we also have to switch these 2, right? So if we switch a pair of these, and we also have to switch the other pair to get it back to what it originally was. So now I'm just going to switch these guys as well. So now 1 is going to be over here, 3 is going to be over here. And again, if you compare it to rotation, that's exactly what we did, and that's exactly the answer that we got, the same, right? So this one for me is easier. I'm just going to move wherever 4 is. I'm going to switch that with whoever's on the dash. Once I do that, I have to switch the other 2 in their position, and I should be good with the sign-in configuration. Okay, so now again, we're going from 1 to 2 to 3. We're ignoring 4. To do that, we move in a clockwise direction again. So this is also R. So all these are kind of boring because they're R. Okay, so last one, we've got actually 2 centers here. So we've got this guy, we've got this guy. I'll start with the center one. Again, I'm going to go ahead and redraw this. We've got OH. There's a hydrogen here. That's implied. If I'm assigning priority, I'm comparing oxygen to hydrogen to carbon to carbon. I can go ahead and draw those carbons in. So carbon versus carbon. Oxygen is number 1. Hydrogen is going to be number 4. But again, we're going to have a tie at this carbon versus carbon. So now, to break that tie, this carbon is attached to a carbon. It's attached to another carbon, and it's attached to another carbon. So this guy's carbon, carbon, carbon. Over here, though, this guy's attached to a carbon, right? It's attached to a hydrogen that's going in, but it's also attached to a nitrogen. So here we actually have, and we're going to list them in order of atomic mass. Let me erase this guy. So this one we have a nitrogen, a carbon, and then a hydrogen. Okay, so again, it's first point of difference. We have a carbon versus a nitrogen, right? Nitrogen is 14, carbon's 12. So this guy gets the higher priority. It's going to be number 2, and this guy's going to be number 3. Okay, and this is a really good example, right? Even though this is carbon, 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 and if you added this up in terms of molecular weight, it'd be like 36, whereas this guy would be like 29, right? It doesn't matter, right? It's literally that first point of difference. That first point of difference is a nitrogen versus a carbon. Nitrogen wins. Okay, so then this guy will be 2. This guy will be 3. 4 is already on the dash. We don't have to do anything to get from 1 to 2 to 3. Ugh, boring. We go in a clockwise direction. So again, that is R. So this guy is R. So now we'll focus on this little chiral center. Again, I'm going to redraw this. And we're going to go ahead and assign configuration. So for this guy, we're looking at a nitrogen versus a hydrogen versus a carbon versus a carbon. Yeah. So nitrogen's going to win. It's going to get number 1. The hydrogen is going to get number 4. Now we have a carbon that's attached to a hydrogen, 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 or carbon that's attached to an oxygen, carbon, hydrogen. So oxygen is going to beat hydrogen any day of the week. This guy's going to be 2. This carbon is 2. This carbon is 3. Okay, so 4 is already on the dash. We don't have to worry about that. But now we get one difference here. To get from 1 to 2 to 3, we go counterclockwise. Counterclockwise. And And that means we are S and sinister. So we have an R here, and then this guy is an S. Okay, so that's that, right? It should be excellent at, why is it doing that? Excellent at assigning configuration at this point, or not really, but at least getting some practice at it helps out. So make sure to email me if you have any questions about what's going on in these practice problems. Okay, so then finally, last little bit here, we're going to integrate this into our nomenclature rules, right? So again, when we talk about these enantiomers, let's take this 2-butanol as an example. So again, with respect to these stereoisomers or these enantiomers, these are molecules that have the same molecular formula, they have the same connectivity of atoms, but they differ about their arrangement of atoms in three-dimensional space, right? So for example, this 2-butanol has a carbon attached to an oxygen at carbon 2, 3, 4, right? There is another way that this molecule can be arranged, and that is this guy, right? Where we have the exact same 1, 2, 3, 4 carbons. We've got an alcohol group attached to carbon 2, right? So both of these are 2-butanol, right? They are not the same molecule though, right? They are non-superimposable mirror images of one another, right? Because they're non-superimposable, they're not the same molecule. So the big idea behind configuration is, number one, we want to give you like a kind of a means by which you can determine the arrangement of atoms in three-dimensional space, and that's what R and S does for us. But we also have to incorporate that into the name of the molecule, right? If I just said 2-butanol, I need to specify whether or not this is 2-butanol in the R conformation or 2-butanol in the S conformation, right? And so how do we do that, right? Well, we assign its configuration via what we just practiced, right? Determining R versus S for whatever chirality center we're dealing with. And then what we're going to do is we're going to put that at the beginning of the name in not Roman numerals, in parentheses and italics, right? So if we went through and assigned configuration for this guy, we would find that this is R. Same thing, if we went through and assigned configuration for this guy, we would find that it's S. They are enantiomers of one another. To specify which one I'm dealing with, I do have to give the configuration of the molecule overall, right? And so I would put that in italics, in parentheses at the very beginning of the molecule. Same thing for this guy at the very beginning of the molecule, okay? Now, if you're dealing with molecules that have 2 chirality centers in them, so for example, if we were dealing with this guy down here, we have 2 separate chirality centers. To denote that, right, we have to, again, put them in italics and parentheses, but to give the configuration for each different center, we're also going to put it with its locant, right? So, for example, at this center, if you guys assign configuration, this is an R, this is an S. If we assign the locants for this molecule, it would be 1, 2, 3, 4, 5, right? That's how when we name stuff, we tell you where it's at, right? We give its locant. So now, to specify which is R and which is S, we're going to put that with the locant of the chirality center, right? So the 2 position is R, there's going to be a comma, the 3 position is S, comma, and then we move on to the rest of the name, okay? You don't have to do that if there's only 1 chirality center, but if you have multiple, you do have to specify the number and the configuration, and then again, separate them via commas. Please don't forget your commas if you need them. Okay, so I don't give you any practice for that, but yeah, I think there's probably practice in the homework, so make sure that if there is a chirality center, you are denoting that in its name. If you do not, it counts off, so just note that.